All right, welcome to Tallest in Physics. So what I'm going to try to do today, I've already collected some data, but I'm going to show you what I'm going to try to do. So here's a mass, and I'm going to twirl it around, and there's a weight at the bottom. So this weight applies a force to this string, and then what I try to do, and I did this previously, is you need to measure how long it takes for that to go around. And it goes too fast for you to measure just one time. So the way that I did it is I just timed 10 seconds and counted how many times it went around. And then I could figure out how long it took to go around once. And then what I did is I have a little black mark on the string, and I can measure how far the mass is to the center of that rotation, and then be able to do some stuff experimentally. So this isn't a perfect experiment, and we're going to see that when I calculate some of the stuff that we calculate. So essentially, from a top-down view, right? From a top-down view, I have this pipe there, and a string stretching out, and this ball, or it's actually a stopper, going around in a circle. All right. So what's essentially my force diagram? It's just the force due to tension. So it's just the force due to tension pointed toward along the string. So it's a tension force. And then I have, so this is not a very good three-dimensional drawing because it wasn't intended to be. I have this mass hanging on the end. And it's a 200-gram mass. I went ahead and actually took its mass to be more specific. It's 198 grams. So that's hanging down. So presumably that's what the tension force is. But we will see there's a couple issues with that assumption, but we're going to make that assumption right now. So if that's the case, I can figure out force due to gravity is mass times g. And if I use 198 and I use 9.8, so 0.198 is it in kilograms times 9.8, since we're doing a real experiment. That equals 1.94 newtons. Okay, so that's the force that's being applied. So what's some of the other data that I collected? Well, what I did is, like I said, it took 22 times for it to go around in 10 seconds. All right, so that is my rate of turning. And then the other thing I measured was to the center of the mass to the rotation point was 22.5 centimeters. All right, so what can I do with this information? Well, what I can attempt to do is, what is the mass of this that's going around? And then we'll see how much error I have, because I anticipate there to be some significant error, and we'll talk about why. All right, so what we're going to use is we're going to use this idea of circular motion. So F net equals mass times velocity squared over the distance, which in this case is force due to gravity. And it's a different force due to gravity. Well, actually, let's say it's tension, and I'm saying tension equals force due to gravity in this case. So I want to know what the mass of that stopper is, because I measured everything else. Or did I? Well, it says velocity, and what did I really measure here? I measured how long it takes to go around one time. So this is actually known as a frequency. Another way to measure this is something called the period. So I'm actually going to use the period instead. So the period is the amount of time it takes to go around once. And so the period would actually be the reciprocal of that. So if it took me 10 seconds to go around 22 times, that's my period. So 10 divided by 22. So it takes 0.45 seconds for that ball to go around once. Well, how does that help me for velocity? Well, velocity is change in distance divided by change in time. We actually know what the distance is because it's a circle. And so one circle is going to be 2 pi r. And the time is this new thing, and it's a capital T to indicate that this is something that happens over and over and over and over again. But it's a very special time called the period. And so then what I can do is I can plug in those numbers. So 2 pi, 0.225 meters divided by 0.45 seconds. So what does that give me? That gives me, let's put that in there, times 2 times pi times 0.225. And so that gives me a velocity of 3.11 meters per second. And I'm keeping these numbers in my calculator so I don't have rounding errors. So I'm going to leave that number in my calculator and bring it over to here. So now what's my, well, actually, I want to solve for m. So why don't I solve for m first and then plug the numbers in? And so in this case, m by itself is going to equal this tension force. R comes on top, and v squared goes on the bottom. Okay, so then mass equals, and we'll put in all these numbers. So we're saying that the tension force is 1.94 newtons. We're saying that measured value of the radius was 0.225 meters. I'm going to use SI units because I have newtons. And so I want to use all standard MKS units, meters, kilograms, and seconds. And then the velocity is 3.11 meters per second squared, which I still have on my calculator. So I will square it and put it on the bottom, and then multiply by 1.94 and multiply by 0.225. And what do I get? I get the mass equals 0.045 kilograms, which is the same as 45 grams. The actual mass of the stopper was actually 38 grams. So it's a little bit off from 45 grams. I suppose let's do the calculation. 45 minus 38 divided by 38. So yeah, it's an 18% error. So why is that? All right, so let's think about why that error is present in this. And so, let's look at the experiment. Experiments are not always perfect. Let me get it to that black line that I did the actual experiment on. And there's a couple things that you should notice, right? So one of the things you should notice is, can I have that string actually perpendicular to that rod? Because that's the way I drew my force diagram. And so the answer is no, that's impossible. Because I have tension force that if it was totally perpendicular, it faced toward the middle of the circle, and then I have gravitational force that goes down. What's my up force? If up equals down, because I'm not accelerating in that direction, I need an up force. So how do we really get it? This is at an angle. Look at that string. There is an angle present. And so there's an angle because that is the string pulls it up to counteract the force due to gravity going down. And then the other thing is the way that this thing's designed. I mean, it's a pipe with a string that is rubbing on the edge of this. Matter of fact, when I try to get this going and I want it to go further out, I really have to get over that static friction, and then I can slow down a little bit and it doesn't suck itself back in. So there's definitely different types of error that occur when you do experiments, and you have to account for that. And so that's why there's a discrepancy there. And I've seen questions on college board exams. Well, I've actually seen this specific thing on a college board exam in the past where you talk about some of the things that can throw your results off. And so we have to think about, there's theoretically things that work really well, and then there's, how are you going to measure it? How are you going to observe it? What are the problems with the way that you're doing it? Is it accurate and precise enough? What other factors am I assuming aren't there that really are there that can cause problems? So anyway, that's an experimental example of how to use circular motion.